In this video, we'll start considering the maximum and minimum values a function of several variables can take. So let me start with the definition. A point AB is a local maximum for the function f of x and y if the value the function takes at AB is greater than or equal to f of x and y for x, y for points that are near AB. So in the neighborhood of the point AB, all values that the function take are less than or equal to that value that the function takes at AB. Okay, so that's a local maximum. Similarly, we can talk about a local minimum. When this value the function takes at AB is less than or equal to the values of the function near that point. Okay, so this is a local minimum. And in this video, we are going to start studying local minimums and maximums and how we can identify these local minima and maxima of a function. Okay, so a simple consequence of having a local minimum or maximum from the single variable calculus is that the partial derivatives at such places must be zero. So a quick result: if AB is a local maximum or minimum, and the function has first order partial derivatives, then these first order partial derivatives at the point AB must vanish. So it's a necessary condition on having a local maximum or minimum. It's not sufficient, but it's necessary to have vanishing first partial derivatives. Okay, and this we can prove easily by looking at what these partial derivatives are. I mean, if we introduce a function of x, a single variable function, by restricting f in the second argument, in the y argument. So if f of x b is what we're looking at, so we keep the y argument fixed at b, then this function has a local max / min at x equals a, and we know from single variable calculus that can only happen if the derivative of this single variable function at a vanishes. But what is that derivative of g at a? Well, it's the partial derivative of f with respect to x at a, b. That has to be 0. And similarly, if you fix the first argument to be the first argument of f to be a and leave the y argument to vary, introduce a single variable function in that way, in y, that function will have a local maximum or minimum at y equals b. So when you differentiate that single variable function at y equals b, you should get 0, and that should give you the partial derivative of f with respect to x at ab. So this is the proof of this necessary condition of having a local maximum or a local minimum. Okay, we call so if we have these partial derivatives vanish at AB, so simultaneously both f sub x and f sub y vanishes at AB, then AB is called a critical or a stationary point. Of the function f. So this is a new definition. So a point is a stationary point if the function's first order partial derivatives both vanish at that point. Okay? So once we have a stationary point, we have a chance at finding a local maximum or a minimum, but it is not guaranteed. And indeed, the way we find or decide whether we have a local minimum or a local maximum, or perhaps neither of those, is using what's called the second derivative test. So this is the generalization of the second derivative test from single variable calculus. So let me say what this test is. The second derivative test can be used or applied once you have a stationary point, AB. So let's assume that AB is a stationary point of f. The function f of x, y. Then the way we apply the second derivative test is that we take the following expression d, which is going to be a number d of AB, which is the following: the second partial derivative with respect to x evaluated at AB times the second partial derivative with respect to y evaluated at AB minus the mixed partial derivative evaluated at AB and squared. Okay? So what we do is we take the product of the pure second order partial derivatives minus the square of the mixed second order partial derivative, and here I assume that these mixed partial derivatives, second order partial derivatives, are the same irrespective of the order of differentiation. So f sub xy and f sub yx is assumed to be the same. So we form this expression, or we compute this number rather, again using the second order derivatives of our function, and depending on this number we have one of two cases first. So if d, this number, is greater than 0 and the second order partial derivative with respect to x is positive, then the stationary point AB is a local minimum. Of f. Second case, if this number capital D is positive, but the second order partial derivative with respect to x at AB is negative, then we have found a local maximum. And last, when this number is negative, we have a stationary point AB that is neither a local minimum nor a local maximum, but what's called a saddle point. This is a new kind of stationary point which this is a stationary point which is not a local minimum or a maximum, so it's not maximal, not minimal in the neighborhood of that point. In the neighborhood of that point, we have points where the function takes greater and also smaller values. So if this happens, then AB is what's called a saddle point. Is a saddle point of F. Okay, and let me now give you 3 examples. So let's consider the function, first the function f of x and y, that is x squared plus y squared. Okay, this is my first example. My question to you is to decide whether the origin point x equals 0, y equals 0, which is a stationary point, whether it's a local minimum or local maximum or a saddle point. What do you think? Pause the video and select your answer below. Okay, I hope you paused it and computed D and found it to be positive at that point, because if you compute the second order partial derivatives of pure partial derivatives of this function, you get 2 for f sub xx and 2 for x sub yy. That multiplied gives you 4, and the mixed partial derivatives vanish. So D for this function is 4, is positive, and also the second order partial derivative with respect to x is also positive, so 0, 0 is a local minimum of this function. Next, let me give you the function f of x and y to be minus x squared minus y squared. And again, pause the video and decide whether the origin x equals 0, y equals 0 is a local minimum, a local maximum, or a saddle point of this function. Okay, I hope you paused it and realized when you compute the pure partial derivatives, second order partial derivatives of this function, you get minus 2 and minus 2, which multiplied gives you plus 4. So again, you are either in case A or B. What differentiates is between them is the second order partial derivative with respect to x, which is minus 2, so that's negative in this the case of this function. So D is 4, but the second order partial derivative with respect to x is minus 2, so that's why we are in this case B. So the origin is now a local maximum. Last, let me give you the function f of xy equals x squared minus y squared, so it's plus x squared minus y squared. And again, you decide whether it's a local minimum, a local maximum, or a saddle point, the origin for this function. Okay, I hope you paused the video and computed this expression and found that now what we have for D is minus 4, because the second order partial derivative with respect to x gives you plus 2, and the second order partial derivative with respect to y gives you minus 2. Those multiplied give you minus 4. So D in this case is minus 4, which is negative. So we are in this third case with the origin being a saddle point of this function. Okay, I hope you enjoyed this video, and I'll see you in the next one.